Next, we are going to discuss about different components of an ion selective electrode. The ion selective electrode is a part of potentiometric transducer. It consists each potentiometric transducer consists of two electrodes. One is a reference electrode and the another one is ion selective electrode. Here the ion selective electrode is acting as working or indicator electrode. So each ion selective electrode it itself consists of an internal reference electrode. Okay, so here see this figure shows an ion selective electrode, and in the middle part, the dark blue color com- part, that dark blue colored part is acting as internal reference electrode, and which consists of a glass tube with different components, which consists of a glass tube, and inside that glass tube there is a silver wire coated with the silver chloride. So there is a thin wire which is made up of silver and which is coated with the silver chloride, and inside that glass tube there is a solution of saturated potassium chloride. A solution of saturated potassium chloride is filled inside the glass tube, and at the end of that glass tube there is porous frit is fitted. Okay, porous frit means it is made up of silica, okay, and some resin part. Okay, silica, which is that frit is made up of silica. So the ion selective electrode consists of an internal reference electrode. That internal reference electrode is made up of a glass tube and it consists of a silver wire coated with silver chloride. The end solution filled inside the solution, which is potassium chloride, and at the bottom of that glass tube fitted with a porous frit. And in addition to that internal reference electrode, a large glass tube, outer glass tube is there in ion selective electrode, outer glass tube part. Okay, that in the outer glass tube part, it is filled with the internal filling solution containing a standard solution of the analyte solution. So inside the large glass tube, it consists of a standard solution of that analyte, which is similar to the analyte solution, standard solution of the analyte ion. And at the bottom side of the outer glass tube, there is an ion selective membrane. That's the name, ion selective electrode. Okay, so on the basis of the type of ion selective membrane which is present at the bottom of a outer glass tube, the type of ion selective electrodes are classified into glass membrane ion selective electrode, solid crystalline membrane ISC, and liquid membrane ISC, then polymer membrane ISE. ISE means here ion selective electrode. So if the polymer or ion selective membrane which is made up of glass, then that type of electrode is called glass membrane ion selective electrode. Suppose it is solid crystalline type, then that type of ion selective electrode is called solid crystalline membrane ion selective electrode. Sometimes it is liquid membrane or sometimes it is polymer membrane. So in each ion selective electrode, the potential developed in the ion selective electrode will be the sum of membrane potential, internal reference electrode potential, and the asymmetry potential. Here the asymmetry potential depends on the nature of the membrane. So ISC. So the total potential of ion selective electrode is equal to E membrane, which is called a membrane potential, then E internal reference, that is internal reference electrode potential, and then E asymmetric, which is mean asymmetric potential. Okay, then again the membrane potential is developed as a result of either an ion exchange process or an ion transport process occurring at the interface between the membrane and inner solution, and the interface between the membrane and the outer solution. Okay, so a membrane is the partition between inner solution and outer solution. So there is a potential difference occur between membrane and inner solution and membrane and the outer solution. Due to this, a membrane potential is developed. So the membrane potential is given by the equation EMN plus equal to RT by N of ln C2 divided by C1. Here C2 is the concentration of the internal standard solution, and C1 is the concentration of the outer or solution is to be analyzed. Okay, so the membrane potential is very important. So the membrane potential is equal to RT divided by NF ln C2 divided by C1. C2 is the internal standard solution, concentration of internal standard solution, and C1 is the concentration of the solution to be analyzed. Then the difference between the ISC. The ion selective electrode has developed a total potential. The total ion selective electrode potential is the sum of membrane potential, asymmetry potential, and internal standard potential. So the net ion selective electrode has a potential now. So then the difference between that potential, the potential of ion selective electrode, and that provided by the external reference electrode, that leads to the total potentiometric or the EMF of that particular cell. Okay, this is the potentiometric readout. This is called the potentiometric readout. So which is directly proportional to the concentration of the analyte. So total EMF of the particular cell depends on the potential of ISC and the potential of external electrode, and then again the potential of ISC is again the sum of membrane potential, then asymmetry potential, and internal standard potential. So the cell which is constructed by the external reference electrode and ISC can be represented below. First component is external reference electrode part, and the second component is ion selective electrode part. In the external reference electrode part, first we place a external reference electrode, then the solution to be analyzed. We have to write the solution to be analyzed. Then the middle partition, which is membrane, and again in the ion electrode part, internal standard solution and internal reference electrode. This way we can represent the ion selective electrode in general. Here the reference electrode shows a constant potential. The reference electrode used here is maybe calomel, saturated calomel, or silver chloride, potassium chloride electrode. It shows a constant potential. So the EMF obtained from the cell will be directly proportional to the analyte ion concentration, or the exactly saying the analyte ion activity. This is all about ion selective electrode. Now let's discuss the types of ion selective electrodes. The ion selective electrodes are classified into different types on the basis of what type of membrane which is present in a particular electrode. Suppose the electrodes may be glass type electrode or glass membrane electrode, then crystalline solids membrane electrode, liquid membrane electrode, or polymer membrane electrodes. So first type of electrodes, which is ion selective electrode, glass membrane type. This glass membrane electrode is used for measuring the concentration of H plus, Na plus, K plus, Li plus, and Ag plus ions. Generally, small cations can be measured by this glass membrane electrode. And the one of the commonly used glass membrane electrode is pH electrode. The glass electrode which is used in pH electrode, that is universal pH electrode. It is made up of a special glass of relatively low melting point and high electrical conductivity. The usual composition of glass for detecting the hydrogen ions, that is in pH electrode, the composition of that glass is 22% Na2O, 6% calcium oxide, and 72% silica. And this composition decides its selectivity towards a particular ion. If it is changed, the composition changed, the glass membrane selective to other ions also. So this composition is very important. And the glass membrane is highly selective to hydrogen ions over a very wide range of concentration. Okay, so the basic exchange reaction which is in glass electrode in the pH electrode is silica, sodium silicate, SiO, and sodium ion. First it is adsorbed with the sodium ion because it contains Na2O, right? So SiO minus Na plus, then it exchanged with the H plus ions. So it converted to SiO minus H plus plus Na plus. So thereby it exchanges H plus ions. So it allows the passage of H plus ions. Then the composition. What are the components in a typical pH electrode? The pH electrode consists of a glass bulb containing a standard HCl solution. See, this is a typical pH electrode. It consists of a glass bulb and which is made up of glass membrane, and this glass bulb consists of standard HCl solution with a zero point 0.1 normality of the concentration. So it consists of a HCl solution, and in which a secondary it and there is an internal reference electrode also there. So see here there is a glass bulb and there is a glass tube, internal glass tube. So in which inside that internal glass tube there is a internal reference electrode, and also there is internal solution. Okay, so then the second component, second reference electrode is incorporated in a concentric glass tube around the main electrode tube containing saturated KCl solution. And inside that glass tube, inside the glass bulb and tube connected to that glass bulb, there is HCl solution, standard HCl solution, and outside which consists of second reference electrode in a saturated HCl solution. And this contains saturated KCl solution. And the contact between this electrode and the test solution is through a small glass frit. See, there is a porous frit in between below. So the below is glass membrane or glass bulb part, and the solution which is filled in internal solution, which is generally HCl solution, and there is an internal reference electrode, and around that glass frit then there is a external reference electrode which is wound around the central glass tube. Then again there is an external solution, okay, solution which is made up of generally KCl solution. The two reference electrodes are normally of silver chloride type. Two reference electrodes are made up of silver chloride. This is a typical pH electrode. And a pH electrode cell can be represented as this form. The left side is indicated the outer reference electrode, which is made up of silver chloride and KCl. So Ag solid bar AgCl solid, then bar Cl minus aqueous. So that connection between that H plus solution and AgCl solution, which is double slash H plus outside glass, then the solution we are going to measure is keep there, right? So that H plus ions outside solution we want to measure the pH. Then double slash which indicates glass membrane, and inside glass there is a standard H plus HCl solution is there, and there is again internal reference electrode which is made up of Cl minus, then AgCl solid and Ag bar. Okay, so the outside glass H plus ion is the solution which we want to measure the pH. Okay, then again inside the glass there is a H plus ion which is the standard H plus ion which is 0.1 normal, which is represented, see here that indicates as 0.1 normal. So this is the way we can represent the cell, pH electrode cell. Then we can calculate the EMF of a particular cell. So the E cell is equal to, we already know that E cell is equal to E right minus E left. Here then we can write it as E cell is equal to E glass. So glass potential. E right here is glass, right? See here inside the glass. Okay, so the glass potential and E glass minus E reference. Okay, so the E cell is equal to E glass minus E reference. And the E glass, we can write the E glass as the potential of glass potential as E0 glass minus 0.0591 pH. Okay, so that pH we obtained that pH is from 0.0591 log concentration of 1 by H, right? 1 by H plus. So log concentration of 1 by H plus we can write it as minus log concentration of H plus, which is nothing but the pH, right? So E0G minus 0.0591 pH, then minus that E reference. By rearranging the above equation, we will get the equation for pH, that is 0.0591 pH is equal to E0 glass minus E cell minus E reference, and again the pH is equal to E0 glass minus E cell minus E reference divided by 0.591. Here E0 glass is a constant for a particular glass membrane. Then E reference is also constant because suppose it is silver chloride or maybe calomel. These two are constant, and E cell we can calculate from the potential, and then we will get the pH value. Okay, so a typical pH meter which do all these calculations, then it shows the final pH reading. So this is the Nernst equation for a pH electrode. Second type of electrode is solid state membrane ion selective electrode. The solid state membrane can be made up of solid crystal, for example, lanthanum fluoride. This type of solid crystal made up of lanthanum fluoride is used for the fluoride ion sensing. Then the second type, either we can use solid crystal or single crystal or polycrystalline material, or otherwise we can use pressed pellet of powdered material. So we can convert a powdered material into, for example, silver sulfide powder into a pressed into a pellet form. Then we can use it as solid state membrane. So this type of silver sulfide can be used. Silver sulfide pellets can be used for sulfide electrodes. Then let's move into the fluoride ion selective electrode. So in the fluoride ion selective electrode, it contains lanthanum fluoride crystal as ion selective membrane electrode. So for example, that solid state membrane electrode. So generally this lanthanum fluoride ionizes as lanthanum fluoride equilibrium with the lanthanum F2, LaF2 plus F minus. So generally the lanthanum F2 plus creates a charge at the surface of that solid state membrane. It creates a charge, that positive charge it will create. So the equilibrium, if both side of the that single membrane, single crystal, the lanthanum fluoride membrane, there is a fluoride ion solution. Outside the membrane, the solution which we want to measure the concentration, and inside there is a standard solution, right? So if the solution, that is the solution, unlight solution, if the unlight solution which contains smaller F minus ion concentration, the potential will become more positive and the equilibrium shifted towards right, because the F minus ion concentration is very low. So the equilibrium tend to produce more F minus ion compared to the inside solution, because inside solution, because the concentration, F minus ion concentration is low, the outside solution is very low, or the solution we want to measure the concentration is very low, so it shifted towards the right. So it becomes more positive relative to the other side of the membrane. So there arises a potential difference. So it is this potential difference across the lanthanum fluoride crystal membrane that is measured, and which is directly proportional to the, or which indicative of the concentration of that fluoride ion solution or F minus solution. Okay, so this is the principle of solid state membrane ion selective electrode. Here on either side of on both sides of this membrane, there exists a potential difference due to the concentration difference. So by measuring this potential difference, we can find the concentration of analyte also. A typical fluoride ion electrode is shown here, which consists of a single crystal or polycrystalline or pressed pellet membrane at the bottom side, and usually an internal reference electrode and internal electrolyte solution also there. Okay, this is your single crystal, or not actually, this is a single crystal polycrystalline or pressed pellet sensor. Next type of electrode is liquid membrane type ion selective electrode. Here in which an ion exchanger or ionophore, here the ion exchanger is also known as ionophore, which is made up of a neutral macrocyclic ion carrier, or ionophore is a neutral macrocyclic ion carrier which is dissolved in a viscous organic liquid. So it forms a organic liquid membrane. This membrane is then sandwiched between two porous partitions. In the porous partitions, ionophores cannot diffuse out of that membrane, but can trap the unlight ion. at the interface between the solution and the membrane. So this liquid membrane can trap the analyte ion at the interface between the solution and the membrane. For example, typical liquid membrane based ion selective electrode, which is used for calcium ion trapping or calcium ion estimation or calcium ion sensing, which is calcium ion selective electrode. Calcium ion selective electrode. Uh, in this type of liquid electron membrane or liquid membrane electrode used for calcium determination is prepared by dissolving a cation exchanger resin or exchanger, which is an aliphatic diester of phosphoric acid, which can be represented as RO twice PO2 minus. So it's a phosphate group. So PO2 minus is a phosphate. So it's a diester of phosphoric acid, where R is an aliphatic hydrocarbon chain in which its length is between the number of carbon atoms is in between 16 and 18 carbons. The membrane is held in a porous compartment between the analyte solution and the internal reference calcium chloride solution. The membrane works by exchange of ions. So here the membrane, that aliphatic diester of phosphoric acid dissolved in a organic solvent, and it is entrapped between porous compartment, then it becomes a membrane, liquid membrane. So this is the representation of that liquid membrane. Liquid membrane is in between that internal reference calcium chloride solution and analyte solution, which contains calcium ions, and that liquid membrane consists of cation exchanger. Here this cation exchanger is capable of exchanging Ca2 plus. So this phosphate group consists of it is protonated. So it consists of H plus ions that can be exchanged by Ca2 plus. So the ion exchanger uptakes Ca2 plus from the solutions into the membrane by the following reaction: Ca2 plus plus 2RO2 RO twice PO2 minus H plus. This H plus ion is weakly attached ions, so it can exchanged with the Ca2 plus. So then it forms when Ca2 plus react with this cation exchanger, then it forms RO twice PO2, then again whole twice Ca plus H plus. Then due to the difference in the concentration after this entrapment, there is a difference in concentration arises. So due to this difference in concentrations of calcium ions on either side of the membrane, potential is developed. This potential developed is directly proportional to the concentration of analyte solution. Here the concentration is Ca2 plus. Then the final membrane, ISA, ion selective electrode, is polymer membrane type ion selective electrode. Ion selective electrode. This membrane is made of by hydrophobic material. Thus, hydrophobic material here used plasticized polyvinyl chloride. So this plasticized polyvinyl chloride is acting as a polymer here, and here in this polymer material an ion exchange material, a liquid ion exchange material, is adsorbed into this polymer material. The important feature of this neutral carrier molecule is its cavity. So here the ion exchange material consists of a cavity which has dimension approximately that of a molecule or ion, which we have to analyze. Okay, so this is a typical construction, typical polymer membrane type ion selective electrode. The lower part is porous hydrophobic membrane, and there is a ion exchange in an organic solvent which is kept on both sides. Then internal reference electrode and internal solution, reference electrolyte solution, and inert fluorocarbon electrode body is there. Then for example, this type of electrode, this polymer membrane electrode, is used for the determination of potassium ions. So in the potassium ion selective electrode, there is the ion exchanger used here is valinomycin. Here valinomycin is used as a ion exchanger, which is adsorbed on the
which is absorbed onto a polymer PVC membrane, plasticized polyvinyl chloride membrane. This is the structure of valinomycin. Here the valinomycin has the cavity, or that inner diameter of this valinomycin molecule is exactly similar to the diameter of the potassium ions. So it can easily trap the potassium ions. The K plus ions are transported across the membrane from higher concentration to lower concentration via the valinomycin molecule. So this method can be very effectively used for the determination of uh, K plus ion concentration. So this adsorption or this transportation of K plus ions through this membrane, polymer membrane, leads to the development of a membrane potential. The outer lipophilic part of the valinomycin makes it compatible with the polymeric membrane and remains strongly attached to it. So, in order to replenish and maintain the concentration of valinomycin in the membrane, a reservoir of valinomycin dissolved in an organic solvent is provided in the outer tube. This is just a construction part, and you have to know the principle behind this. So this is about ion selective electrode. So there are four types of ion selective electrode. One is polymer membrane type ion selective electrode, then liquid membrane type ion selective electrode, then solid membrane type, solid state membrane type, then again further glass membrane. Okay, glass membrane type ion selective electrode. Next, we need to ascertain the performance of an ion selective electrode by measuring some of the parameters like sensitivity, selectivity, detection limits of a particular ion selective electrode. So, first we need to determine the sensitivity of an ion selective electrode. What is meant by this sensitivity? Sensitivity is nothing but the change in measurement signal or change in the signal uh, per unit concentration. Here, this potential determination potentiometric sensor, which follows generally it follows an Nernstian response. If an electrode or if a sensor is said to be follow a Nernstian response, then that electrode follows Nernst equation. The potential of an ion selective electrode depends on the potential of an ion selective electrode depends on the logarithm of the ionic activity of an analyte according to Nernst equation. That equation is given below. E is equal to E0 plus 2.303 RT by NF log A. Here A is the activity of the analyte. So in general, a potentiometric sensor, it's EMF of a cell, that ion selective electrode, EMF potential of an ion selective electrode is related to the log of activity, log A. In the above expression, that term 2.303 RT by NF is termed as slope factor. For example, at 25 degrees Celsius, that is 298 Kelvin, the slope factor for potassium ions, in which N is equal to 1, the slope factor is equal to, if we substitute all the values for R, T, N, F, then we will get the slope factor as 59.16 millivolt MV. And suppose the ion selective electrode is expected to show Nernstian response, that is the Nernstian response is an ideal slope behavior for each tenfold change in a monovalent ion concentration. The ISE potential will show a change of 59.16 millivolt. If any potentiometric sensor, if it follows Nernstian response, this will be the behavior of a potential, that kind of potentiometric sensors. That is, any ideal slope factor, any Nernstian response showing ion selective electrode, each tenfold change in the concentration. That is, if suppose initially the A value is 10, then tenfold change means if it becomes log 10 is equal to 1, right? So if it changes to 100, suppose a tenfold change in concentration occurs, then initially it is 10, then after if it changes to 100, then what happens? 2.303 RT by NF log 100 is there. So log 100 is equal to 2. So before 10, log 10 is equal to 1. So the slope factor is equal to 59.16. Then tenfold change in concentration results only twice, that is 2 into 59.16. So every tenfold, if suppose if it is 1000, then what happened? Log 1000 is equal to 3. So again one more 59.16 millivolt change only occur. So its a slope factor is very low here. The measurement of slope factor gives an indication of the performance of the electrode system. So every electrode system, the measurement of this slope factor is very important. Then this slope factor measurement is done by construction of a calibration curve. The construction is similar to your potential photocalorimetric calibration curve construction. So a calibration curve, what is meant by this calibration curve, that you have to know. Standard solutions of different concentration of the analyte solution have to be prepared. Here in addition to that, we need to add some ionic strength adjustment buffer in order to become that activity and concentration uniform or identical is added to each standard solution. So first you have to prepare different standard solution and add ionic strength adjustment buffer to each standard solutions. Then EMF of the ISE or reference electrochemical cell in each standard solution is measured, and a plot of EMF versus log of analyte ion concentration is constructed, which is the calibration curve. Okay, so the right side there is a calibration curve is given. In x-axis log of activity or log concentration. Generally concentration is expressed using activity. So log A in x-axis and E potential in millivolt is expressed in y-axis. So the Nernstian response here is the ion selective electrode is expected to show Nernstian response over a given range of activity, in which a plot of EMF of cell versus log of gives a linear relationship. Uh, where are the regions in which it shows Nernstian response? Then that region is linear relationship. So here the log A and E is in linear format. So then if the plot is linear, then it follows Nernstian response. So this calibration curve is also used to determine unknown analyte concentration, also similar to your photocalorimetric estimation. Then the next is determination of detection limits. Detection limits, already you know that detection limit is the concentration of the ions below and above which the ion selective electrode does not give reliable results. Generally this detection limit is used to mention the lowest level or below which an ion selective electrode does not give reliable results. So from the calibration curve, generally a calibration curve look like a curve which is given below. So only above that line it gives a linear relationship, below that line which doesn't give any linear relationship, and it is look like this. So if we plot a slope and we connect these two lines, then we will get a limit of detection. The practical limit of detection may be taken as the activity of A at the point of intersection of the extrapolated linear segments of the calibration curve. Generally, a calibration curve consists of two lines. One is a linear log A and E relationship, linear relationship with the log A and E, and another line which is parallel to log A is obtained. So if we connect these two, then a slope, which is we can draw a slope. So if we connect that two line, then we will get a limit of detection or detection limit. Then the determination of selectivity. So first is sensitivity, then detection limit, and then third point is determination of selectivity. So the ion selective electrodes are selective but not specific. So it can be selectively analysis or selectively determined a group of ions. The ion to be determined is referred to as the primary ion. Okay, and the other ions which is called interfering ions. Suppose the major ion to be determined is primary, and the other unwanted ions we can call it as interfering ions. The preference of an electrode for the primary ion over the interfering ion is called the selectivity of the electrode. So selectivity is the preference of an electrode for the primary ion over other interfering ions. Suppose, in order to take into account the response of the electrode to an interfering ion, an additional term is incorporated in the Nernst equation. So, the Nernst equation will convert to, or it takes another form called Nikolsky-Eisenman equation. Okay, so that equation is E cell is equal to E0 plus 2.303 RT divided by NF log in square in bracket Ca plus K AB, then Cb. Here Ca and Cb is the concentrations of the analyte and the interfering ion respectively. Ca is the analyte and Cb is the concentration of the interfering ion. And both have charge Z, and Kab is the sensitivity coefficient. Here Kab is the, not sensitivity, selectivity coefficient. Selectivity coefficient. The selectivity coefficient Kab is a numerical value indicating how well the electrode can discriminate the analyte ion against the interfering ion. If Kab is very small, good selectivity is obtained when the selectivity coefficient is sufficiently low. If Kab value is very small, which indicates good selectivity. So what happens if Kab value is very small, maybe 0.0001, then that Cb part will be, we can neglect that Cb part, and the total part only consists of Ca. When compared to Ca, the Cb part we can neglect. So the interfering anion part we can neglect. The smaller Kab values, the less impact the interfering ion will have on the measured potential. If Kab is very small, then less impact of the interfering ion will have on the measured potential. For example, less than 1, then the Kab values are that electrode potential only depend on that concentration of analyte, does not depend on the interfering ions. If it is greater than 1, then what happens? Its concentration, unwanted ion concentration also interfere in the total potential. So selectivity will become very low. For example, in the case of analyte ion, K plus analyte ion, K plus in valinomycin, the interfering ion may be Na plus can act as interfering ion, Ca2 plus, Mg2 plus also can act as interfering ion. In the case of, for example, in the case of K plus, if Na plus is acting as interfering ion, its Kab value is very small, 10 raised to minus 4. So its selectivity is much high. And again the Ca2 plus Mg2 plus, if it is act as interfering ions, the Kab values again varies very small. So the selectivity of K plus in the presence of Ca2 plus is very very high. And again in the analysis of Ca2 plus, the Mg2 plus Mg2 plus can act as interfering ion. Its selectivity is comparatively less. Because its Kab value is only 0.02, and again in the analysis of Ca2 plus, K plus ion also can act as interfering ions.